If a membrane is permeable to only one type of ion, then the movement of ion will result in generation of a potential difference across the membrane, and magnitude of this potential difference can be calculated using the Nernst potential. But what will happen if more than one ion is permeable? And in a cell, there are many permeant ions. For example, sodium is the major extracellular cation and potassium is the major intracellular cation. And let's consider anions to be impermeant in this example. Sodium, if it is allowed to move inside, it would enter inside the cell and it would generate a positive potential inside. So at around plus 60 millivolt, membrane will attain equilibrium. This is the Nernst potential of sodium. And potassium, if it is allowed to move, it will go outside down its concentration gradient and it will develop a potential difference whose value is minus 90 millivolts. Let's say this is a Nernst potential of potassium and this is Nernst potential of sodium. But what happens if both sodium and potassium are permeant ions? Both the ions cannot reach their equilibrium potential. The resultant membrane potential will be decided by the permeabilities. If both have equal permeability, the membrane potential would come to an average value of the two values. Let's see this in a linear scale. So this scale shows membrane potential from minus 90 to plus 60. If potassium is the only permeant ion, then the membrane potential will be just as minus 90. But the cell also has another ion, sodium, equilibrium potential is plus 60. If the membrane is equally permeable to both the ions, then the membrane potential somewhere will come in between the two. So the average of these two is minus 15 millivolts. If potassium has higher permeability, the membrane potential will move towards potassium, and if sodium has higher permeability, the membrane potential will move towards sodium. In a typical neuron, the permeability of potassium is higher, so the membrane potential is close to the potassium. Even if there is more number of ion, if we know the value of their permeability, the intracellular and the extracellular concentration, we can calculate the membrane potential of the cell. There are two different equations to calculate that. The first is GHK equation. Here we need the permeability value of individual ions and their intracellular and extracellular concentration. This is a simplified version after adding the gas constant and the body temperature and the Faraday's constant. And the other equation is chord conductance equation, which uses the similar property called as the conductance of ions and the total conductance and the Nernst potential of individual ions. Conductance is the movement of charges across the membrane when there is a potential difference. As the permeability is the ability of the ion to move across. So both the equations will yield the similar results. The membrane potential is different from the equilibrium potential of most of the ions. So the individual ions are not in equilibrium, which means they are continuing to move across the membrane. So the potassium ion, only if there is minus 90 millivolts inside, it will be able to stop the movement of potassium ion. Since this is only minus 70, potassium would continue to go outside. And sodium would also continue to enter inside the cell. If the ion movements continue for a long period of time, concentration gradient itself will change. And the Nernst potential value is decided by the concentration gradient. So the Nernst potential itself will change and it will influence the membrane potential also to change. In a cell, the concentration gradients are maintained by active transport mechanisms. The sodium potassium ATPase maintains the potassium and the sodium values, the concentration in the cell, and thereby it maintains the Nernst potential and eventually the membrane potential also. Since energy is required to maintain, we call this as a steady state, and individual ions are not at equilibrium. For certain ions like chloride, the permeability is very high in certain cells like skeletal muscle, and it does not have any active transport mechanisms to maintain concentration. So chloride would continue to move till its equilibrium potential becomes same as the membrane potential. So chloride ion, instead of influencing the membrane potential, it adapts to the membrane potential. Its equilibrium potential becomes same as the membrane potential. We can imagine this has a tug of war between the ions, and the strength of their pulling is decided by the permeability of the ions. The ion with the highest permeability pulls the membrane potential towards its equilibrium potential, and the impermeant ions does not contribute the magnitude of the membrane potential. And if an ion permeability is 0, then we can remove it out of the equation. I would like to discuss another concept called as driving force. This gives us the magnitude and the direction of ion movement across the membrane. This is the difference between the membrane potential and the equilibrium potential of ion. So for potassium, it is the difference between the two. So this is minus 70 minus of minus 90. So this would be plus 20 millivolts. So plus 20 millivolts is the driving force for potassium. Sodium's equilibrium potential is far away from the membrane potential, so it has a huge driving force. Minus 70 minus of 60, this would give us minus 130 millivolts. So this magnitude gives us net electrochemical driving force of the ion, and the sign would tell us which direction the ion would move. Is positive for a particular ion, then a positive ion, it means it would go out of the cell, and if it is a negative ion, it would enter the cell. And for example, sodium, it is negative. So sodium is a positive ion, so it would enter the cell, and if it's a negative ion, it would actually go out of the cell. So by calculating driving force, we can calculate net electrochemical gradient, which is moving the ion, and also the direction of the ion movement. Thank you.